time. I want to keep us moving as we're starting basically this session. Well, good morning, good afternoon, good evening, everyone. Thank you all for participating in today's webinar hosted by Mitacs, discussing quantum materials and their implications for quantum technologies, more innovation and commercialization prospects. We have 4 distinguished guests and panelists today. Each will be providing a very brief overview and presentation of their activities, the centers they're representing, and the research fields in the area of quantum. We will follow our conversations with a Q&A, a brief Q&A shortly after the presentations, where I'll be posing some targeted questions to our panelists. And we would like to ensure that we keep enough amount of time at the end of the session for our audience, for all of you participating, to directly post questions for our individual panelists. I will invite you to post your questions directly in the chats, and we will be monitoring the chat, and I'll be basically posing the questions to our panelists, essentially. Without further ado, I would like to start with brief introductions of all our presenters, and then we'll just go on with the presentation schedules as planned. My name is Iman Yahyai. I'm Director of Major Accounts with the Mitacs organization based in Toronto, and I'll be having the pleasure of hosting the session today. On the panel, we have 4 distinguished guests. I'll just go in a row and making a brief introductions, and before handing them the floor for making the presentations. We've got Dr. Adina Luican-Mayer. Adina is a professor of physics department at the University of Ottawa, an associate professor. She received her PhD in physics from Rutgers University. And prior to joining U Ottawa, she was a postdoctoral fellow at the Center for Nanoscale Material at Argonne National Laboratory. She's a recipient of U Ottawa Faculty of Sciences Early Career Researchers of the Year in the year 2020, Ontario Early Researcher Award in 2021, and she's a CFAR Fellow of the Quantum Materials Program. She held the NSERC Training Program Materials for Quantum Technologies, MacTech, as well as the NSERC Alliance Quantum Consortium, programmable quantum simulators based on 2D material. Thank you, Adina, for joining today. We also have Dr. Louis Taillefer. Louis is a professor of physics at the Université de Sherbrooke in Quebec, where he leads a research group specialized in the experimental investigation of quantum materials, such as superconductors and metals with strongly correlated electrons at very low temperatures and in high magnetic fields. He received a number of awards, including Killam Prize in Natural Sciences in 2012, the Simon Memorial Prize in Low Temperature Physics, Kamerlingh Prize in Superconductivity in 2018 for pioneering experimental work in superconductivity. In particular, the discovery of multi-component superconductivity, quantum oscillations, and quantum critical points in heavy fermion and copper oxide semiconductors. In 2021, Louis was elected Fellow of the Royal Society. Thank you so much, Louis, for also joining us and for agreeing to do a presentation to our audience today. Next up, we've got Dr. Andrea Damascelli. Andrea is a professor and scientific director of the University of British Columbia's Stewart Blossom Quantum Matter Institute, or QMI, very well known to the quantum audience. He's a professor at the UBC's Department of Physics and Astronomy as well, and a Tier 1 Canada Research Chair in the electronic structure of quantum materials. And also, he's a co-director of the Max Planck UBC at Tokyo Center for Quantum Materials. As QMI's scientific director, Andrea led UBC's efforts, resulting in the $66.5 million award from Canada's first Research Excellence Funds, or CFREF, for quantum materials and future technologies. With more than 150 papers published, more than 19,000 citations, and an H-index of 59, Andrea's work on quantum material has gained global recognition and helped position Canada as a leader in the field of photoelectron spectroscopy. Thank you, Andrea, for joining as well. Last but not least, we've got Dr. Nathan Nelson-Fitzpatrick. Nathan is a director of Quantum Nanofabrication and Characterization Facility, QNFCF, at the University of Waterloo. His associations with QNFCF began in 2012, initially contributing as a process engineer during the concluding construction stages of the facility's principal clean room within the Quantum Nano Center. Over the year Dr. Nelson-Fitzpatrick has fulfilled various roles in process engineering, culminating in his appointment as a director of the lab in 2022. Under Nathan's leadership, the QNFCF has evolved into a pivotal research platform offering access to an extensive array of over 100 scientific fabrication and characterization instruments spread across several laboratories. Annually, the facility accommodates over 230 unique users, supporting a wide range of innovative research activities in the field of quantum and quantum materials. Thank you all for joining today. I'm going to delegate to our individual presenters to kindly share their slides for the presentations one after another, starting with Dr. Taillefer. If you don't mind unmuting yourself, sharing your screen, and take us on. Approximately, we are timing about 10 minutes per presentation, and I will kind of provide a 2-minute warning towards the end. The floor is yours, Dr. Taillefer. Thank you.
Thank you very much, Iman, for giving us this opportunity to discuss quantum materials in the Canadian context. For my case, I will mostly focus on describing the role of 3 actors in the quantum materials field: Institut Quantique in Sherbrooke, the Quantum Frontiers Lab, collaboration between France and Sherbrooke, and the Canadian Institute for Advanced Research, CIFAR. But let me start maybe by saying a little bit about my own research. I have an experimental group at the University of Sherbrooke. We study a variety of quantum materials, in particular, these 3 types here. So we're interested in superconductors. We're interested in what we call strange metals, and I'll say a little bit about that, and also spin liquids. The kind of phenomena that we're trying to elucidate, understand, are this so-called pseudo-gap phase, which is perhaps the most enigmatic phase of quantum matter that we know in these so-called cuprate superconductors, the most robust superconductors known today. We're also interested in this intriguing phenomenon called Planckian dissipation and in strange metals, and I'll say a few words about that later on. And finally, our most recent interest is what we call chiral phonons, the fact that phonons are sensitive to magnetic field. So in our lab, we specialize in what we call transport properties. We measure the conduction of heat and the conduction of charge, typically down to very low temperatures, approaching absolute zero, and also in very large magnetic fields, typically amongst the largest fields one can reach in the lab anywhere. So our lab is housed in what we call the Institut Quantique. So Institut Quantique is a new institute that was founded more or less simultaneously with the CFRF award that Sherbrooke obtained in quantum science and technologies, and this inaugural competition at the same time as the CFRF award at UBC that Andrea mentioned. This is our new building, a few years old, and it's just a wonderful place to meet and exchange. About 30 people, researchers, are part of the Institut Quantique, and they basically take part in one of 3 pillars of research: so quantum materials, quantum information, and quantum engineering. The Institut Quantique is at the heart of a growing, vibrant quantum ecosystem in Quebec. I won't go through all this, but there are established quantum companies like QuanQubit, Pascal, IBM Quantum that are part of this ecosystem. Also, a number of startups are being launched in this very supportive ecosystem, and other partners. So maybe I can mention just one example of a young startup that began just a couple of years ago. It's called Chemia Discovery. It was It was launched by Amireza Atay, my PhD student. And here, the mission of this startup is to accelerate the discovery of new materials. And in the field of quantum materials, the real driver of discovery, of advances are new materials, and they're constantly coming online. And so this startup, the aim of the startup is to really accelerate the discovery of different types of materials for different purposes, different technological applications. So I encourage you to visit their website if you want to know more. I'd like to also say that in Canada, one of the characteristics of the field of quantum materials is a very good level of collaboration amongst the universities. And this is just one example of a recent collaborative effort between our group at Sherbrooke and colleagues in Toronto and McMaster. So we got together and succeeded in getting this $12 million CFI grant this year. So with which we'll be able to equip our labs and collaborate. For example, by having samples made in Toronto and McMaster being supplied to us in Sherbrooke for measurements and so on. At Institut Quantique, we've identified 4 major challenges, scientific challenges, and you can see that on our website. And one of them has to do with is called Planckian dissipation. It's part of this project on cuprate superconductors. And here, let me tell you a little bit about this. In conventional metals, if you measure the electrical resistance as a function of temperature, you find that it varies as the square of temperature. But in certain metals called strange metals, in fact, what's found is that the temperature dependence is perfectly linear. Sometimes it undergoes superconductivity, but you can continue to follow this T-linear resistivity to T equals 0. And basically, it appears that this is the manifestation of a new fundamental law of quantum physics, whereby electrons would scatter at the fastest rate they can, dictated basically by Planck's constant. So this is one of the topics that in my group we're very interested in. Another organization that I'm involved in and I'd like to mention here is a lab called the Quantum Frontiers Lab, which is an international research lab. The acronym is IRL, created by the French CNRS, but based in Sherbrooke, and the purpose of which is to foster collaborations between in the field of quantum materials and quantum information between Sherbrooke and various labs in France. And I can say more about that in the question period. But let me just mention one of the activities that the IRL organizes are international summer schools, and our next summer school will be in Cargèse in Corsica in June 2025. So I'll be sure that you hear about this in due course. An example of what came out of this France-Canada collaboration is work that my group has done over several years with Cyril Proust in Toulouse. And in Toulouse, they have some of the largest, the most powerful magnets in the world, enabling them to reach fields of order 90 Tesla or even higher. And so that turns out to be very, very useful for us if we want to study the behavior of electrons in these cuprate superconductors by suppressing superconductivity. And this allowed us a few years ago to identify a key signature of this mysterious so-called pseudo-gap phase by going to very, very high fields. Another application of these high fields is to suppress superconductivity so that we can track the resistivity down to very low temperature, as we did here in the field of 55 Tesla. And lo and behold, find that we have these perfectly linear temperature dependence of the so-called strange metals. So this is Planckian dissipation. Then you mentioned that a few years later than the creation of the IRL, now a new network has been created called CAFCA, Canada-France Quantum Alliance. And it involves a number of universities in France, 8 universities in Canada. And perhaps Adina will say a few words. She's leading the organization of our second workshop. The first one was in Paris last year, and this year it's in Ottawa in May. And the idea is to foster collaboration more broadly with all of Canadian researchers through this network. The last organization I'd like to mention is CFAR. This has been a major player in the field of quantum materials. The quantum materials program was created something like 35 years ago, and it brings together not only researchers in Canada, but researchers across the planet. And at the moment, there are 30 members or so, and in the US, UK, and Germany, Japan. And the key, the success of this program has really been, has come from bringing together the three types of expertise that are fundamental to quantum materials research, namely materials synthesis, experiment, and theory. So, and Adina and Andrea are both part of that program. So I think my time has run out. I was going to mention some examples of what the fruits of such collaborations. For example, with Brad Ramshaw, a colleague at Cornell University, or collaboration with a theorist, Subir Sajdev at Harvard, on these chiral phonons, and I can say more about that in the question period if someone is interested. So let me stop here and pass over to you, Iman.
Well, thank you so much, Andrea. Luis, sorry. Yeah, time is a bit crunched, but we do have quite a good buffer towards the end of the session for questions. I do invite audience to post questions at that time in the chat, and some questions are already actually coming in the chat. I'm monitoring the chat for sure, but thank you so much for the presentation. We have next up Adina, if you don't mind sharing your screen and starting your presentation as well. Thanks again, Anne.
I hope that this is all good.
It's all good. Yep.
Great.
You're seeing it. Thank you so much.
Great. Yeah, good afternoon, everyone, and thank you to the organizers for putting together this venue to share our thoughts on quantum materials. And thank you for all participating, and Lee for the talk before. So I'll keep it pretty short in this presentation, but I guess I'll pick up on Lee's last point, and the take-home message from my presentation. What I want to underscore is the value of having multi-institutional partnerships in order to be effective at training and innovation in quantum science, and particularly in quantum materials. So I think in particular in Canada, we're a relatively small community. And so what I want to highlight today in this presentation is how having the means to engage in this multi-institutional collaborations and partnership can be very impactful. So for the last, I would say, about 5 years or so, a number of us sort of geographically, making sense in Quebec and Ontario, we would often find ourselves in, the situation of having student exchanges or sending samples from one lab to another, calling each other up if you have a great undergrad to do graduate school. And so very organically and very naturally, it was obvious to us that it would be great to get together, to have an umbrella under our team, and to get together and do these activities together. And so luckily, NSERC does have such a funding source. It has this type of a program, CREATE. And so we sort of put our ideas and our thoughts on paper. And as of last year, we're happy to be having this program and to work together, to collaborate, and to most importantly, educate the next generation in quantum materials. So I want to talk to you a little bit about this now. So broadly speaking, the mission of this program is to train the future Canadian workforce in quantum, and to try and bridge this gap that trainees often have coming out of an academic research in environment and going into industry or to other type of jobs. And so the program is emphasizing training in material science and engineering, recognizing that these are really pillars that drive a lot of the quantum field. And so Of course, not just technical training, but in addition to that, supplemented by information to the students or training of the students in things like entrepreneurship or ethics, or things that are relevant and really makes them prepared to enter the workforce wherever they choose to work. So the team that we put together in this training program, I've shown before the names of my colleagues from University of Ottawa, Toronto, McGill, Polytechnique, Waterloo, and Sherbrooke. And I thought it would be fun if I kind of just took the the section in our proposal that talks about our expertise and did a word cloud. And wouldn't you know, quantum materials came out highlighted. But that's just to show you the breadth of expertise that would typically come together, and that comes together in this program to train the students. So we have, for example, Tami. She's a theorist that works with topological material. Hae-Young works with a lot of magnetic materials, also a theorist. Thomas and Peter at McGill. Thomas is in electrical engineering, and Peter is a physicist working with different techniques such as transport or scanning probes. Stephanie is a new hire at the University of Ottawa. She does artificial intelligence for quantum materials. And then our colleagues at Polytechnique, Stefan and Osama, again, bringing this interface between science and engineering, in particular, also on semiconducting systems. Adam, like myself, is a condensed matter physicist working on 2D materials. And then our colleague, Andrea Marie, who is who's a theorist that is really expert in understanding correlated electron systems using computational approaches. And our colleague Lee, who's an experimentalist, also working in transport. So really a breadth of expertise that is getting together to help our students get training broadly in quantum materials. So I want to give you a highlight of an activity that we do. It sounds very broad, but just to make it more concrete, one of the activities of this training program is a summer school. And so in our vision, this particular summer school that we've developed moves around to a different location every year. And so as you see geographically, we are in these different regions. And so the idea is that we want to leverage the local ecosystem, and the student that would be involved in this program for, let's say, 3-4 years, by the end of this program, every summer, they would have had the opportunity to move around and see different facilities and different expertise at the different universities. So as I've mentioned, in addition to technical lectures, posters, flash talks, it also has components that educate the students on topics such as entrepreneurship, where we do outreach. And so currently, our summer school is planned for May 2024. This program is very new, so we're just starting to ramp up the activities. And the first location is Toronto, so we're very excited to join forces with CFAR Quantum Materials, the program that we mentioned before that several of us overlap with. And we're very pleased that we were able to join forces. And one of our special highlights is that we'll be actually visiting the Acceleration Consortium at the University of Toronto, and we'll learn a little bit about something we don't have in our program, but exists there, which is how to use artificial intelligence to drive innovation in quantum materials. And then also, again, part of this community spirit, this summer school is followed by a broad Quantum Materials Canada conference at the University of Toronto. So the students will be participating in all these activities, will be engaged and immersed in this learning environment, and we hope that this will really help their training in quantum materials. As I've mentioned, this type of training programs, this is just an example. There are several across the country. This is just the one that that I happen to lead. So these programs are also embedded in local ecosystems. So just to give you an example of the type of things that around our university you may find, we have institutional quantum institutes such as NextQT at the University of Ottawa, and the others that will likely be mentioned in these talks. Innovation zones, right? Trying to translate these basic science into technologies, and as well as large-scale facilities or existing regional networks that facilitate interactions and collaborations. And so, of course, we want to leverage all the time all these existing resources and connect them to our training program. So the second part, I want to turn from training and getting resources together to train the workforce in quantum materials to innovation and science. So I am myself, as the introduction, mentioned, I'm a professor at the University of Ottawa, and I'm trained as a condensed matter physicist. My lab works in quantum materials, and in particular using scanning probe microscopy to study quantum materials, as well as to develop and characterize quantum electronic devices. And so just one slide about my group's background. So we study materials, low-dimensional, two-dimensional materials in particular, and their quantum properties at the interfaces and at the surface, such as moire. Heterostructures, as we study atomic defects and how we can create and understand their properties locally, topological materials, and so on. So recently, through collaboration with the National Research Council, we also try and develop quantum circuits. And also another part of our research activities is to use these quantum materials and 2D materials in particular for applications that have to do with energy, environment, or security. And so recently, for example, as a highlight, we've been working with the Department of Defense to try and develop chemical noses. So this is a kind of a broader portfolio of what we do. At the University of Ottawa, our research activities, this is our group, and our research activities happen in these brand new buildings, the Advanced Research Complex and the STEM Complex, as well fortunate to be equipped through CFI grants. This is our particular lab with our scanning probe microscopy capabilities, ultra-high vacuum and low temperature. And we're really so fortunate at the University of Ottawa. I guess we'll hear more about such capabilities at Waterloo. We're so fortunate to have also a nanofabrication facility. So this is the expertise that we have at the University of Ottawa. And again, in the spirit of multi-institutional collaborations that can drive innovation, we got together as a group through the Alliance Quantum Consortium to put together a program where we want to use 2D materials as a platform for quantum simulation. The idea being that in order to build a quantum simulator, there are several existing platforms. So first of all, what is a quantum simulator? So oftentimes we try and describe materials using a paradigmatic Hamiltonian. And so those are turns out those are very hard to solve. But what you can do is you can actually try and mimic them through a certain system, and then you can try and solve that idealized mimicked system. So cold atoms have been used for that, and other such systems. And in this consortium, we propose to use a platform based on 2D materials. So first of all, we want to use the fact that twisted 2D materials form this array of moire patterns as a quantum simulator. In another thrust of our consortium, we want to actually build sort of point by point, qubit by qubit, if you like, a quantum simulator in semiconducting 2D materials. And in a third thrust, we actually want to develop wafer scale techniques of growing 2D materials. So this is actually a capability that exists at the University of Ottawa. So my colleagues in this consortium are involved in the various aspects of this work. And this is a partnership with industry as well. I guess we'll probably mention a little bit further in the webinar how exactly we connect to them. So perhaps I'll keep here my overview, and then we can continue in the discussion session.
Thank you so much, Andrea. Perfectly on time. Appreciate your slides. Great presentation. Questions are already rolling in, and thank you all for submitting questions as well. I'll make sure to address them to the participants accordingly. A bit of a housekeeping note, as I posted in the chat, when posting questions either directly in the chat or in the Q&A session, please also indicate who should the question be addressed to so we can coordinate accordingly. Next up, we've got Dr. Andrea Damascelli, who's going to start presenting and then talk a little bit about his work and his activities at QMI. Andrea, floor is yours.
Thank you, Iman. Thanks so much for this opportunity. Thanks, everyone, and for being here. Good morning, good afternoon. And what I'll do today, I'll talk about activities that go on in the Stuart Blossom Quantum Matter Institute here in Vancouver. But the Stuart Blossom Quantum Matter Institute is also the home to the Max Planck UBC University of Tokyo Center for Quantum Materials. So to some degree, what I'm going to tell you today in terms of our activities bridges both of those initiatives. The mission of the Quantum Matter Institute is really quantum materials by design. So basically, what I really like to emphasize in this talk is that quantum materials should really be seen as an enabling technology. As such, they are really the building blocks for future technologies. And again, in this particular role, they're really central to the National Quantum Strategy of Canada. So really, in terms of enabling all kinds of applications in many different areas. You can see here the mission of the center. This is very strongly linked to the funding from the Canada First Research Excellence Fund that came in a few years ago in 2015. And that really, the idea was to bridge the fundamental work on quantum materials with future technology that would have an impact on the quality of life. The mission basically brings in these three pillars: research, training, and translation. So really, the fostering the discovery of quantum materials, but also all the way to devices, training the quantum workforce that we need so much in Canada, and then transfer, of course, this knowledge and expertise to industry. The way we organize our work at QMI was around grand challenges. So as the Institute grew up, we really worked on developing a research strategy. And this research strategy is centered around three of these grand challenges. You see them listed here. The first one, and I'll say a few words about each of them later, and really highlighting how we can go from the fundamental work in this area all the way into technological applications. First one has to do with 2D materials. We've seen some of that in Adina's talk, so engineering exotic phases in these kind of systems. The second one really approaches the design of materials from an atomistic view, and with emphasis on the role of disorder. So the interplay between correlation, topology, and disorder in all of these materials. And the final one has to do with quantum information, and this particular challenge evolved from taking an approach of what can be really done with realistic quantum computation today, particularly in the area of quantum materials, but now going into really pushing materials that can sustain and deliver very strong, very robust quantum coherence. So the issue of overcoming decoherence. As for who are the people in the Institute, we're looking at about 250 people altogether, spanning physics, chemistry, and electrical engineering. So all of the aspects that come into this effort, and of course, theory and experiments. You're seeing here a large cohort of students and postdoctoral fellow, approaching 200. We have 25 faculty members in one building here in QMI, in the Institute on the UBC campus, and 4 of them are affiliate members across Canada, and one of them is even in Europe. One key aspect I really like to highlight is the number of staff members we have. So scientific and technical staff and operations staff, you're going to see some of their contribution later in the presentation, but really this is crucial when you have a research effort that really has the ambition of having impact on technology. You do need professional staff to support the effort. As far as what QMI does, I mentioned the Max Planck UBC University of Tokyo Center, which is housing QMI. Here you see the map of the collaborations that we are involved with. Of course, Max Planck and Tokyo are prominent, both in terms of the number of people going back and forth, but also of the number of collaborative projects which have come out. But of course, that's as far as collaboration, QMI is pretty much engaged with many of the activities in North America, and Europe, and Asia, and South America. I'd like to highlight in particular work with the Flatiron Institute and the Rice Center for Quantum Materials, 2 strong players in our research work. Okay, let me now give you an example of the three grand challenges, and what do I mean when I talk about enabling technology, what is really enabled by these new materials towards novel technological development. I'm showing here a device made of those exfoliated materials that Adina has been referring to. So you can, these days after the discovery of graphene, so single layer of carbon atoms exfoliated from graphite, this approach has been taken to many different materials. And so now you have a wide range of heterostructure built by exfoliated layers, so monatomic layers, say, stacked on top of each other, potentially with twist angles also being controlled. And here's one particular device worked on by Ziliang Yi, one of our young faculty members in QMI, and together with collaborators both in QMI and also University of Tokyo. And this is really a device for photovoltaics type applications. So basically, conversion of light, so photons, into electrical energy, but now done with these novel materials, which allows you small scale, ultra fast and high efficiency, as we've never seen before, and operating at room temperature. So this is really enabling now a technology, perfecting a technology, and really enhancing a technology. Even more exciting is the work that where you can do that really lead to technological application that did not exist before. And that's perhaps the power of quantum materials and the great promise of quantum materials. I like here to highlight work that was done in QMI, led by Marcel Franz, who, as in addition to me, is also one of the CFAR member in UBC. And this has to do with now high temperature superconductivity, and in particular, high temperature topological superconductivity. And how this is being achieved is by taking the high temperature cuprate superconductors, as Louis has introduced, exfoliating them, and now having two monolayers of those materials brought together with a 45 degrees twist angle. And here you can see the superconducting order parameter of the two materials now being coupled with a specific geometry, and this can lead to what is called topological superconductivity at very high temperature. And the beauty, or really why this is interesting, is because topological superconductivity could bring in an additional form of protection in addition to superconductivity, also the topological nature of this new device, which could be used for topological quantum computation, for instance. So really robust quantum coherence. This work has been then picked up, and in fact has been funded by the Moore Foundation in the EPICS program under the leadership of Ziliang Yi, bringing together a number of us, including, of course, Marcel, who's the proponent of the idea to really go and realize in practical terms topological superconductivity at high temperature. Now, this is one direction which is into the quantum information and novel architecture of quantum information, but this kind of approach really can have more direct ramification in the direction of devices and immediate. First of all, I'd like to highlight that new work by Philip Kim, and again with Marcel Franz as a collaborator, that really demonstrate that superconductivity topological at high temperature can be realized in a system like this. So this particular work, if following up the proposal, the theoretical proposal, is the demonstration that topological devices are possible. The next one is work led by me, together again with a team at UBC and with Xanadu Quantum Technology, now taking these exfoliated materials and using them as a platform to realize single photon detectors at very high temperatures. So using this system to push the technology to high temperature and the sensitivity to extremely high value to the point of doing photon counting down to the single photon. Another example I'd like to mention is the one of design of materials with attention to the role disorder. This is an effort led by Alan Hallas, yet again, a CFAR member here in UBC QMI. And her work has to do with a new form of engineering materials using disorder, and in particular, entropy as a way of engineering these materials. What does it mean, disorder, in this case? Well, here is an example of what she's working on. So a system, which is actually a crystal, well ordered as far as the structure is concerned, but now you can see color-coded, each of these sites contains a different transition metal. So disorder means having 5 different transition metal on a particular site, and in fact, letting entropy drive this to reach an equilibrium state and a more stable material. And for what kind of application? Actually, a wide range. Here in particular, one which has to do with batteries, where you see number of cycles, the performance of the battery over cycle. You see that generally materials will decay over time, but here is one particularly that retains its stability and is resilient basically over time. And this is where the highest entropy has been realized. So disorder is a way of creating very stable material for novel application, something which has been immediately being picked up by the community and also the private sector. I'd like to mention that her work now is really pushing into the direction of the discovery of novel quantum materials for a wide range of application, and she has been leading an international group that brings in QMI, but also Max Planck and University of Tokyo, as well as McMaster and Bruce Golan for a 7.3 million CFI project for the discovery of materials from all possible approaches, all the way into the high pressure discovery. Finally, when it comes to quantum applications for quantum computing, I like to mention 2 particular points. One is GeoSelfie in the Alliance Consortium, bringing together 5 different universities in Canada and companies for spin qubit type application. And again, going back to Marcel Franz, here is where when you look for long coherence time, the daemon actually so-called come to the rescue. A daemon is actually a transport, which is a qubit, a superconducting qubit, but now based on a junction between a D-wave superconductor and an S-wave superconductor. With this, I'd like to basically conclude in a couple of more slides. One is mentioning what Dana will tell you about more in the future is the Quantum Collaboratory, bringing together Sherbrooke, Waterloo, and UBC with world-class expertise, state-of-the-art infrastructure. And I'd like to highlight a challenge here. This is to support the quantum community in Canada in doing their state-of-the-art kind of work. And the challenge is really retaining and attracting, first of all, attracting that expertise, so the people, and retaining those people. And this is a real challenge for us, given that we have competition for the rest of the world, in particular from the US. You're going to hear, from Nathan, but advanced nanofabrication facility like this one will play a key role in the training of personnel. Here are some of the numbers that go through UBC, but no huge numbers, and play a key role in commercialization. Here is Matthew Mitchell, former postdoc at UBC QMI, and now a sort of employed by Green Photonics, one of the spin-off of QMI into translation to technology. Finally, I'd like to mention that, of course, this is very relevant to private sector industry. Many companies come in as users, and in fact, it goes well beyond the quantum world. Here you see companies like Accelera Biotech or the Center for Brain Health at UBC. So really it's very wide impact that materials and enabling technology have from the quantum world all the way to all kinds of fields, including medicine. With this, I'd like to conclude. Thank you.
Thank you so much, Andrea. Fantastic presentation. I have to say that I had the pleasure of meeting your postdoc or Mitacs Award winners, Dr. Mitchell as well. Fantastic work that is coming out of QMI. Thank you for that presentation. Without further ado, I'm going to just move on to our next distinguished speaker, Dr. Nelson-Fitzpatrick, who's going to talk a little bit about QNFCF at the University of Waterloo. Nathan, the floor is yours. And yes, we are seeing your full screen. Thank you.
Okay, wonderful. Thanks, Iman, for the opportunity to speak here. I guess this dovetails really well with things that Andrea was saying. So yeah, first off, I'd like to just I guess present our little piece of the quantum ecosystem in Canada, the Quantum Nano Fabrication and Characterization Facility. So at Waterloo. So this advance. So what is the QNFCF? So basically we're a core nanofabrication and characterization lab. A lot of universities will have a similar resource. Adina was talking about the resource at Ottawa. Andrea was talking about the resource at UBC, and of course there's a very good fab at Sherbrooke as well. So what do we do as a core facility? We exist to professionally manage state-of-the-art kind of high-tech tools and enable access to a wide array of researchers who can't necessarily host this in their own individual labs. So I like to list kind of, well, what why do you organize tools this way? Why do you house them in this way? So we aim to provide a range of well-maintained tools, basically have professional staff, who are here every day, who are intimately aware of the tool. There's continuity. They're able to keep these pieces of equipment going for their entire useful lifetime. Furthermore, we can build up and communicate and maintain stable baseline processes so that individual grad students coming in and out of the lab don't necessarily have to reinvent the wheel every time they come. Every time we have a new graduate student. We provide equitable access to all the resources under our control, and basically we charge a fee for access in order to defer maintenance costs. So in order to pay for service contracts, repairs, etc., we charge an hourly fee for access. So why is this interesting to this panel? So QNFCF is, like many fabs, but we're actually our history is really quite intertwined with the Institute for Quantum Computing at Waterloo. So IQC was established in 2002 originally, and then as IQC staffed up with experimentalists, they realized they needed to establish their own fab facility. So that was us in about 2008. And then the rest of the University of Waterloo community kind of saw the quality of the infrastructure that was being developed and wanted access. And eventually we got reorganized under the Office of Research centrally in the University of Waterloo. You know, that being said, because of our history, our tool set, you know, and our geography, we're tightly intertwined with the entire quantum ecosystem in Waterloo. And you can see this this poster I stole of the quantum ecosystem in Waterloo. We have labs located in this IQC building, and then our historical labs in the RAC buildings. And I'll talk a lot about different capabilities in those two locations. But anyways, the current kind of snapshot for operations today is that we manage about $68 million worth of investment in equipment and facilities. And last year, we're almost done with 2024, our fiscal year, but our last fiscal year, 2023, we had about 240 unique users across 78 different groups. About 3/4 of those people were from the University of Waterloo. A pretty heavy contingent of small and medium enterprises who are accessing these resources, and then a few people from other universities who are traveling to us to access this equipment. We invoiced over 36,000 hours of individual equipment use, generating about $1.5 million of revenue to support lab operations. And our lab is pretty extensive. We have actually 12 full-time staff members. We work closely with David Corey's group to actually help him enable people to access those advanced capabilities. That adds up to another 50 users from 18 different groups and another $250,000 of revenue. And we've had tons of support from all sorts of different players locally in Ontario and then from the Canadian government. So I'm going to have to move maybe a little bit quicker if I'm going to stay on time. Well, what makes our operation unique compared to other fab facilities? Waterloo is a really generous university in terms of IP policy. So it makes it very easy to form agreements with external companies or researchers because the IP is essentially owned by the researcher. Unique to our model, I like to say that we strive to build a community of lab users. We do all our training one-on-one, delivering over 1,200 person hours of training last year. About 98% of the tools that we manage over 140 tools, are available for training, and we have rigorous onboarding and process control to make sure that tools aren't inadvertently damaged. We host regular workshops, we host lunch and learn events. We try to encourage as many collisions as possible between individual researchers because that's how a lot of progress is made. And I like to say that we co-locate the sort of typical enabling tools of a fab alongside cutting edge quantum tools that are maybe not so common to get access to. So one of those capabilities, and I saw some reference to this in other slides, is a brand new 2D materials fabrication lab capability that we just launched actually last week. And I don't think I need to work too hard to motivate this. Definitely a number of previous talks were speaking about these 2D quantum materials, these sort of exotic materials that, sort of been played with after graphene. But we've built a lab basically copying a setup from Adam Sen's group, who Adina was speaking about, and then integrating a number of other tools with that into this large array of glove boxes so that 2D materials can be exfoliated, and then lithography can be performed, and then film deposition can be performed to generate electrodes for devices, and subsequent plasma etching or characterization can be done, all without leaving an inert environment. And this is to enable the exploration of 2D materials that are, not air sensitive like graphene, alongside other 2D materials to form heterostructures with twist angles. So I just have a few close-up shots of some of the workstations before they went into the glove box assembly last month. So we have this microscope with with a heated stage and a micromanipulator to enable very precise pick and place location of graphene flakes. I saw a very similar example in other facilities, but here we have it organized in such a way that someone doesn't have to rebuild this on their own if they want to start exploring these material systems. We've also in the same glove box assembly, we've added electron lithography via dedicated SEM and patterning engine, and integrated deposition chamber as well. Some other advanced materials capabilities that you could access through QNFCF. So this is David Corey's multi-cluster UHV molecular beam epitaxy tool. So I sort of motivated this by saying superconductors are kind of the original quantum material, but this type of tool enables the deposition of superconductors, magnetic materials, insulating materials with very precise control on thickness and with isolated dedicated deposition chambers, so that these processes don't interfere with each other. And this is a capability we've had at Waterloo for more than 10 years now. And this has been sort of managed by David Corey and his group. And we work very closely with them to enable, basically to leverage the platform that we've built for the fab to enable outside access to tools like this to external researchers, to companies, without the need to actually do a formal kind of collaboration. And on the right is the dedicated technical staff for this tool, Saba Sadehi. Within our cleanroom facility, we also have a quantum flavor to the tool set. So we have some dedicated PVD systems for superconducting processes. I put that these are more production ready in quotes because these are sort of a little larger tools, enabling slightly larger wafer sizes and sort of moving these very advanced film capabilities a little closer towards a production scale. So we've got an E-beam evaporator dedicated for Josephson junctions with in situ oxidation and superconducting aluminum deposition, alongside this Plassey sputter system with niobium, niobium nitride, and niobium titanium nitride capabilities, which is very similar to a system you can access in the fab at UBC. And lastly, I want to point out we also have ability to access an ARPAS system, and this is a capability that Saba Sadehi has worked on and learned a ton from the expertise at UBC QMI through the Quantum Collab. And I feel like I'm probably out of time, so I'm just going to wrap it up with just a closing slide. So thank you.